The learning target for today is to solve problems using tangents to circles. So your essential question, I will solve problems involving tangents to circles. Now there is an absolute ton of vocabulary in this unit, all right, and all of the vocabulary is quite important. It's particularly important that you pay attention to measurement relationships and notation as we go through this. The set of all points in a plane that are equidistant from a given point, called the center, is a circle. All right, when we draw circles, we always include the center point. Now, if this center point was labeled A, for example, I could note this in a proof or in my work as circle A. So just like you use a little baby triangle or a little baby rectangle as a symbol for those particular polygons, for a circle, we use the circle with the center in it so that you can tell the difference between a circle symbol and a zero. The distance from the center of a circle to a point on the circle is the radius. You should remember that from elementary school. The radius is lowercase r. A segment whose endpoints are the center of the circle and a point on the circle is also the radius. Two circles that have the same radius are congruent. The distance across the circle through its center, the diameter. Again, something you should remember from elementary school. And diameter is lowercase d. A chord that passes through the center of the circle is also a diameter. A segment whose endpoints are on the circle. That did not come out well at all. Let's erase that. Maybe I should actually pick up some decent circles here. So if we go from A to B, and we are not going through the center, it's just a plain chord. Chord AB, make sure you have the line segment symbol above it. Let me come up here and make this diameter CD. Again, the line segment symbol above it. A line that intersects a circle in 2 points. So in this case, and let's move that down a little bit. Okay, so we're going to have a line that intersects in 2 points. I'm trying to make this look a little better than how some of them are looking. Okay, this is a secant. Edit. Nope, go away. Okay. Secant. Now, secants can be segments because segments are part of lines. So if I make this AB, this one happens to be line AB. All right. A line that intersects a circle in exactly 1 point, and I'm just going to pick up another color here. This is a tangent. Okay, in this case, line CD. Again, tangents can be line segments. It all depends on what's drawn for you. Okay. Coplanar circles that intersect at exactly one point. And let's do this. There we go. They are tangent circles. Whoops. Because you only have one point where they intersect. Point D up here, just going back, sorry, I got a little distracted, but point D is the point of tangency. Okay, coplanar circles that have a common center. I like these. Oops, didn't draw that well. Concentric circles. Why do I keep doing that today? All right, next page. A line or segment that is tangent to coplanar circles is called a common tangent. So let's get a couple circles going. Let's do a small one. Let's do a bigger one. And no, I'm just going to draw these. Okay, I can have what's called an external tangent. Well, you got to pretend that's a straight line. Let's erase that. I did not do a good job on that at all. Okay, try again. There we go. This one happens to be an external tangent because I never cross a line that would connect the center point of each of these circles. I can also have what's called, sorry guys, I can also have what's called an interior tangent, internal tangent. You're just going to have to pretend I actually managed to draw that straight and hit it. Okay, the red one's an internal tangent because if I connected the centers of these circles with an imaginary line, I'm crossing that imaginary line. So we have common tangents. And they can be interior or exterior. All points on a plane inside the circle are interior to the circle. All points outside are exterior. And the point at which the tangent intersects the circle is the point of tangency. I talked about that on the previous page. All right, so let's take a look. We have some theorems. I know how much you love your theorems. They make you so happy. And notice that none of these have names. Always fun. If a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So my perpendicular is right there. It's really easy when you draw these to make it look like the right angle is actually at the center of the circle, so be careful. If L is tangent to circle Q at point P, then QP is perpendicular to L. In a plane, if a line is perpendicular to a radius of the circle at the end point of the circle, then the line is tangent to the circle. So theorem and its converse, you could write this as a biconditional. So if L is perpendicular to QP, then L is tangent to circle Q. Next one. If two segments from the same exterior point, which in this case would be point S, are tangent to a circle, then they are equidistant. So, if SR and ST are tangent to circle P, then segment SR equals the length of segment ST. Very helpful. Next, let's identify some circle parts. Alrighty, we have C as the center. We have a diameter of EG. We have a radius here of CG. You have a chord, FH. Okay, we have a tangent line, line AD, or line AB is tangent. You have a secant, FH. Notice the notation there. When I talk about line FH, I'm talking about a secant, but when I talk about segment FH, I'm talking about a chord. Okay, B is a point of tangency. You could go so far as to say that A and D are exterior to the circle, C and J are interior to the circle, whereas E, B, F, G, H are on the circle. All right, now word problems like this one, they will definitely be on your first quiz for this unit. You are standing at R, 4 feet from a fountain, and we are going to assume our fountain is a circle, since that's what we're talking about. Should have actually included that, but here we go. Circle. And we are at R, 4 feet away. The distance from you to a point of tangency on the fountain is 8 feet. I didn't draw that well. We're going to pretend that's our point of tangency right there. This is 8 feet. Alrighty. What is the radius? Remember that that has to be, the point of tangency has to be my right angle. See what I mean about my drawings often looking inaccurate? The right angle is not at the center. The right angle is actually at the point of tangency. So when I look at this, right, I'm using Pythagorean theorem. A squared plus B squared equals C squared. Well, my A is X, and my B, in this case, is X plus 4. And it's going to equal 8 squared. Right? So x squared plus x squared plus 8x plus 16 equals 64. Let's see, 2x squared plus 8x minus, okay, 16 minus 64 is 48. All right, so a little algebra. Your quadratic has to equal 0 before you can do anything with it. You have to pull out the greatest common factor, x squared plus 4x minus 24. Now let's see, negative 24, let's see, we've got 1 and 24, 2 and 12, 3 and 8, 4 and 6. Oh, I did this entire problem wrong. So, and we're too far into the notes for me to go back and re-record them. So I'm going to erase. I hope you were using pencil, because I just realized I drew this entire problem incorrectly. So let's go back. This happens. All right, I am, got a radius. I've got a point of tangency. I have R. This is 8, this is 4, this is x, this is x. What I did wrong was x plus 4 is my hypotenuse. So x squared plus 8 squared should equal the quantity of x plus 4 squared. This is my hypotenuse. I must pay more attention. So x squared plus 64 equals x squared plus 8x plus 16. Subtract that out. 8x equals 48. X equals 6. So the radius is 6 feet. Didn't remember making that problem that complicated. AB is tangent to circle C at B, and AD is tangent to circle C at D. Now, we had a theorem that said two tangents drawn from the same external point were equidistant. So that means x squared plus 24 has to equal 49. So x squared will equal 25. X is going to equal 5 with negative 5 as an extraneous solution, and we weren't given any measurements, so that's good enough. We've got AB tangent to circle C at B and AD tangent at D. Find the value of x. Again, they will be equidistant because they are tangent from the same external point. So let's make this equal 0. 5x squared, the 4x's cancel out. 18 minus 27, 45. 5x squared equals 45. Wow, this one's nice. X equals 3 with negative 3 as an extraneous solution. Divide by 5, you get 9, then take the square root. Okay, you need 2 questions and a summary.